Okay. Welcome, Gaurav, and thanks for joining today. Today we have Dr. Gaurav Vats. He is currently leading a European Commission funded project, which is Marie Curie Actions Individual Fellowship, with support from Catholic University in Belgium and Lumpes Corporation, Switzerland. He is developing novel synaptic technology based on electric oxide on neuromorphic computing. He got bachelor's and master's from IIT Mundi, and he got PhD from South Wales, Australia. He has authored more than 30 research articles with prime contribution in the area of solid state thermodynamics, energy conversion, low energy optoelectronics, as well as integrated photonic devices. He is a recipient of UMSW Dean's Award for Best PhD Thesis in 2020, IUFFC Student Award 2019, at ISAF Conference in Switzerland, UNSW Faculty Science Award in 2017, and Institute of Engineers India, Young Engineers Award 2016-17, and Indian Science Congress Association Young Scientist Award 15-16, and one more Bombay Postgraduate Research Award 2015. During his PhD, he was also awarded with top of scholarship by Australian Institute of Nuclear Science and Engineering, an independent research grant from China and NT Berlin Foundation, Finland, 2019. So obviously, he has a lot of accomplishments. So we are very happy to introduce and let's listen from him about what he has contributed and what he wants to do in future, collaborate with Penn State University. Welcome.
Well, thank you for the nice introduction. Let me make it full screen. So today I'm going to talk about this light-assisted parametric domain switching for controlled modulation of current. So let's begin this talk with a few applications that has been proposed. For example, in this first one, electro-optic modulators using ferroelectrics have been demonstrated. So here they apply electric field using these gold pads, and because of that, the domain population in this barium titanate layer changes. And as a result, the light modulates in this silicon waveguide, which is just above it. Another application is this optical frequency shifter. So basically, they made these IDTs which generate surface acoustic waves through these ferroelectrics, and this was used to modulate light, which was coming from here. Another application is photovoltaic effect and energy harvesting. So in this particular paper, these guys showed 100% quantum efficiency. Another interesting application here I have shown is this optoelectric memory. The concept was proposed back in 1978. It was patented on another material in 1993. And in this figure, you can see there are various states that have been written on bismuth ferrite-based memory. So it was electrical writing and optical reading using the ferroelectric photovoltaic effect. Definitely, there are a lot of opportunities with ferroelectrics in this domain of optoelectronic devices. What people have been doing is they are trying to understand how it works. For example, in this particular case, they did a synchrotron measurement on a barium titanate crystal, where they showed that with light, this intensity of A and C domains, A and B domains varies. So you can see by turning the light on, it goes up, and off, it goes down. So you can control the domain population with this, and they suggested that it is coming from a ratchet effect across the domain walls. Okay, and then this another example where this young and Alexei showed that we can achieve reversible control of current polarization in BFO. So here they shows how it was looking before illumination and after illumination, and they explained it using the tip enhanced photovoltaic effect. So a lot of similar things are going on with new interesting applications coming up. For example, this is not working now. Okay. For example, in this particular case, they developed this device, optoelectronic synapses, which is good for neuromorphic computing. So they used two different materials. One is PZT, which is not so sensitive to light, and then this tungsten sulfide layer on top of it, which is sensitive to light. And altogether, this device worked well, and it was shown that it can act as an optoelectronic synapses. Now, if we want to have similar kind of applications, it would be best to have a single material that is ferroelectric as well as sensitive to light. And this is the kind of material which I will be talking about. And that's this KNBNNO, which is sodium potassium niobate with 2 mole% barium nickel niobate. This material was introduced by my friend and collaborator, Dr. Youngbai, in 2017. The beauty of this material is that this is a polycrystalline material with a band gap of 1.6 electron volts. It shows above band gap photovoltages, and it is good ferroelectric. So, for example, in this figure D, if you focus on this dark curve, polarization versus electric field, you can see it is showing a nice polarization hysteresis curve. And when I expose this to a wavelength of 445 nanometers with very low energy of around 5 milliwatt, then the loop expands a bit. There is a change in the torsive field and the remnant polarization. It looks a bit leaky as well, but we'll come to that in a bit. So in today's talk, I'm going to explain some of the experiments and conclusions we made on this material. I'll be talking about optoelectronic modulation of current. There is an analogy between optical and electrical poly in this material. We'll talk about possible reasons for that. And very interesting is the cumulative effect of light and electric field, followed by mechanisms, applications, and conclusion. Thereafter, I'll talk about optomechanical mapping of ferroelectric domains and their impact on the photovoltaic response. I'll cover the effect of electromagnetic. I'll cover a bit of literature, effect of mechanical stress on the material topography, reversible mechanical control, and optomechanical control of domains. So let's begin with this part A. So before we start, I would like to give you a glimpse of this piezo response force microscopy. That's the technique that I have used throughout these experiments. So in this technique, basically we have a cantilever which is in contact with the material surface. Now, ferroelectric can have polarization pointing up or pointing down. When this cantilever is in contact with the sample, we apply an AC bias, and depending on the direction, it either expands, the domains either expands or contract, due to which the cantilever moves up or down, and we track the movement of this cantilever using the photodetector. So by this, we can actually map the ferroelectric domains in any material. For example, here I am showing you the domains in PZT by BCO heterostructures. So in figure A, you can see the topography, which is basically the surface. And then in figure B, you can see this phase image, where the meaning of this color contrast is domains, whether they are out of plane or in plane. Sorry, they are pointing up or pointing down. So for rest of my talk, I'll be showing the phase images, and the only interpretation is the direction of the ferroelectric domains. That's what you can understand from the color contrast. At the same time, we can also acquire PFM amplitude, which is an indication of the piezo response of the material. Yeah, so let's look at some of the results. So before that, I should explain what actually I did. I had a ceramic sample, which was 100 microns thick. I put that sample somewhere here and an AFM tip in contact, and I use a laser source to shine light on the sample. And that's what I was doing. And firstly, I did this electrical pulling experiment. So you can see this figure A. This is the image I acquired in dark. Again, this bright yellowish domains and dark domains means polarization pointing up and pointing down. I pulled the whole area with +4, and I acquired the image of the same area again. Now, if you look at any of these features, for example, this one, you can see that bright yellowish domains are expanding. I did the same thing with the negative bias. And here you can see that these bright yellowish domains are actually contracting. And in some places, they are broken into two. For example, if you focus on this feature and see this, it's broken into two domains. Interesting point is I mentioned that this was a 100 micron thick ceramic sample, polycrystalline ceramic sample, and I'm applying very low voltages, +4 volt. And this kind of measurement can be done even with lower. I tried up to 0.5 volts. If you imagine the electric field I'm applying, it's not that high. And with that field, I'm able to move the ferroelectric domains, which is interesting because now we have low voltage switching or low voltage movement of ferroelectric domains. And we have this expansion and contraction of domains rather than total flipping, as I showed in the case of PZT in the previous slide. So it's not switching fully, but the domains are moving. This kind of behavior I also observed in skin layered NBT-BT samples. So the idea is the sample, few top microns of the sample are showing this kind of skin layer. That's the terminology used, and they behave in this way. However, let's just focus on this again. After this electrical polling, I tried optical polling of the sample. So what I did, I acquired an image in dark, no light was shining. I did nothing, it's the pristine image. And then I shine light on the sample, same wavelength 405, and the yellowish bright domains are shrinking again. If you compare any feature, you'll be able to see the differences. So clearly there is some analogy between optical and electrical polling. We'll come back to that in a bit, but let's try to understand why the material is showing this optical movement of ferroelectric domains or optical switching. So literature suggests there could be possible reasons such as localized heating. That means light is causing a heating, which causes diffusion of elements, and that causes movement of ferroelectric domains. There could be structural changes. So if you imagine the structure, there could be an octahedral tilt, there could be a change in oxidation state of the central atom, there could be a lattice relaxation. Third possibility is charge compensation. So the idea is when you shine light on the surface of the material, it generates charges on the surface, which are compensated by the movement of ferroelectric domains. Let's look at these possibilities one by one. First is localized heating. So I acquired this temperature dependent PV loops, and you can see there is a slight change in the remnant polarization, whereas almost no change in the saturation polarization. At the same time, I use the same laser to directly measure the temperature change on the surface of my material, which was around 1 degree centigrade. So it's very clear that my laser was not causing heating, and even if it is causing heating, it's not enough to bring a change. Let's look into the other possibility, structural changes. So what I did is I performed this neutron diffraction experiments at Ensto in Australia. So I acquired a pattern in dark and another in light when the sample was exposed. And you can see there is slight change in the intensities of a few peak. Few are going up and few are going down. I mean, we are still analyzing these results, but the problem is either these changes are coming from an error from the instrument, or probably there are no structural changes. Or there is a possibility that structural changes are so small that our instrument could not measure them. So for the time being, we are ruling out this possibility as well. Now to study the third possibility of charge compensation and change in surface potential, I use this technique, Kelvin probe force microscopy. So in this, what I do is we have a cantilever. I bring it close to the sample at a height of say Z. It could be somewhere between 20 to 50 nanometers. It experiences an electrostatic force which we try to balance, and we call that potential as contact potential difference. So this contact potential difference gives us an idea of the surface potential, and we can estimate the work function of the material as well. So here I have shown this measurement on a test sample, which is HOPG. So we use this to calibrate our measurements. Now let's see what I got with this technique. So this is the surface of my material. I was scanning like this. So you can see this is the fast scanning direction. This is the slow scanning direction. At the same time, I was acquiring this contact potential difference. So again, this direction. So in this figure C, what I did is I started the measurement in dark. No light was shining on the sample. And at this point, where you see the yellow color appears, I exposed it to light while performing the measurement. And you can see the color changes. This contrast means the potential is higher. And at this point, I turn the laser off and let it relax. I did the same measurement again and again with different wavelengths, 405, 500, and up to 700. And you see this line, this white line. I've just plotted the profile of this white line here. So you can see whenever I was shining light, the surface potential increased. It was consistent. After turning the laser off, it went back to the original position, but there is some sort of time dependence, which could be useful for some of the applications. I repeated the same measurement here with different wavelengths in one go, and you can see the maximum response is for 405. That means the sample is sensitive to the whole visible range spectrum, but the maximum response is to 405 because light absorption is maximum for this wavelength. Again, at this point, we can conclude that this change in surface potential is compensated by the movement of the electric domains. And that's why we see the shrink of those yellowish bright domains. So till this point, we have established what is happening in the sample because of the laser exposure. I also did the same measurement macroscopically to avoid any confusion. So I had a sample which was not cold. I kept it into this white light, like this white light in the room, for 8 hours, and we got a little bit of a piezo response from the material. That means the material was cold. Then we pulled it electrically in dark. We got a piezo response. Then we did the same thing, same parameters, same voltage, same time, but white light was also shining on the sample, and we see a difference here. So that means light is helping in pulling the material. Then we did electrical polling. The sample was fully pulled in one direction, and we shine light in the opposite direction, and we could actually depole the sample as well. So here we are showing that we can actually pole and depole sample with light exposure. Now let's look at the cumulative effect of light and electric field. I previously mentioned that there is an analogy between the two. This is very interesting, and let's see the first result. So again, I acquired this image. This is the pristine image, bright and dark domains, two types of domains. Then after acquiring this image, I put my AFM tip somewhere here at the center. You can see this white dot here. My AFM tip is around 30 nanometers in diameter. And if you look at the scale, this is like 2 micron by 2 micron area. What I did, I shined a light for a few seconds. I applied voltage for a few seconds, and I turned both off. And I acquired the image of the same area after doing this light and +4 bias at this single point. You can see there is clearly a difference. These yellowish bright domains are shrinking throughout the whole area, while I applied voltage at this single point in the center of this image. Now, let's see what happens when we use a -4 bias, basically different direction. So I acquired this image, which is pristine. The scale is bigger in comparison to the first figure. So it is like 4 by 4 micrometers. Again, I place my tip at the center. I shine light. I applied -4 volts for a few seconds, and I did the measurement again. You can see the domains are completely flipped. So you don't see any yellowish colored domains here. So there is a large area switching within a few seconds. And I was wondering how big this change could be. I scanned the nearby area. Again, the scale is different here. It's around 30 by 30 microns. And I got this weird shape. I repeated this measurement again and again with different light intensities and electric fields. And I got different kind of shapes. And I was thinking what exactly is happening here. At the end, I was able to figure out that my AFM tip was somewhere here, and this was the laser spot size. So what is happening is, when I shine light, the conductivity of this particular area is tuned. It's enhanced by a few orders. And when I apply electric field at this particular point, it's spread over the whole area. And you see a large area switching, or I can say ultra fast movement of ferroelectric domains. And this is really interesting. This kind of things have been reported in the past, in 90s and 80s on lithium niobate, but the required voltages and light intensity was too high. But here we are playing with very low voltages and very low energy laser. Now let's look at the current, what is happening. So in this first case, I acquired this current density with time. So here, no current was flowing through the sample. I turned the laser on, there is a photocurrent. And then I applied +4 volt. Because in the beginning, I showed that light and positive bias works in an opposite manner. So the direction of current is flipped and it reaches here. On turning the voltage off, it goes back. we see the photocurrent, and then finally it goes back when I turn the light off. With the negative bias, I see some photocurrent on turning the laser on. On applying a -4, it goes all the way up here. There is time dependence. And then on turning off, it goes back. And if you look at this units, there is a difference of a few orders. So in this case, light is actually supporting the applied negative bias, and in this case, it's opposing the negative positive bias. And using a combination of voltages, we can have any intermediate state here, and we can also play with the light intensity and the laser spot size, which is interesting for applications such as neuromorphic computing or memoristic applications. So that's what we did. Let's look at the mechanism of this. So I acquired this transmittance data, and here we are playing with this 405 nanometers wavelength, which is somewhere here. See the zoomed version here, and you see there is almost no change between the fold and unfold sample. That means this 405 is fully absorbed by the sample. When the light is absorbed, there is a change in the conductivity, which we could measure. And this change in conductivity with applied voltages and the in-plane, with the in-plane electrodes was going like this. And with out of plane, it's going like this. You can see the behavior is not linear, but it's slightly non-linear. And we try to understand it with this. So light absorption causes photoconductivity. There is charge collection faster in presence of applied electric field because your domains are more aligned in one direction, and there is more charge collection. Effect is not cumulative, and it's non-linear. So here is an exaggerated schematic of what is possibly happening in the sample. When you shine light, the charge carriers goes from valence band to the conduction band. There could be an intra-band transition because the sample shows the bulk photovoltaic effect. As it is a non-centrosymmetric sample, there is a variation in the distribution of the charge carriers. And with applied field, we have more flow, which is leakage from here and here, and that's why we see all this. Now, with this understanding, let's try to see if we can have some applications. So here are a few results. So I pulled the sample. I was measuring the photocurrent. These are microscopic measurements, by the way. So I can see the photocurrent here, here, here. It's consistent. And in dark, when I just applied the positive bias, you can see how the electrical current was there. With the negative bias, again, I could see some electrical current. These are in opposite directions. Again, the negative bias is having same direction as the photocurrent and opposite to the positive. So in this figure D, what I did is I started in dark. I applied a voltage +1, it goes here. And on shining the light, it goes up. And I repeated that. But with a lower voltage of +5 volt, it was here. And on shining the light, it went in the opposite direction. So you can actually stop the flow of current by doing this. So this is very interesting because that could be used as a diode or some other application. In this case, I have only showed modulation of photocurrent. So there was a photocurrent which was modulated by applying positive and negative bias. And you can see the modulation is asymmetric in the positive and the negative direction. Finally, I showed this, you see these black dots. They are the AC current that I could see from the sample when no light was shining. And when I shine light, there is an asymmetric rectification of the AC current. So that's another possible application. So far, the understanding is this material is sensitive to the visible light spectrum. The charge carriers generated by the illumination are compensated by the movement of the electric domains. Light behaves analogous to electrical polling. And we can say here is, we are having an ultra fast and ultra large domain switching. We can modulate the photocurrent, electrical current. That means we can use this material as a photodetector, electrical modulator, and even a light effect transistor. So in this kind of thing, we have a source, a drain, but no gate. Light acts as a virtual gate. So yeah, and another interesting thing is photocurrent can be controlled by the state of polarization in D33. So if you look at this figure, I polled sample at different parameters where I could observe different D33. And then I checked photocurrent in these samples. The photocurrent is different in different samples with different polarization. So this is interesting. And when we talk about D33, basically we are talking about electromechanical coupling. And that's what I'm going to talk about in part 3 of this talk. So let's move on to part B. Let me show you a few recent examples. So in this first example, there is electromechanical coupling between photovoltaic effect. So what these guys did is they apply stress on a centrosymmetric crystal. It's not ferroelectric, it's not piezoelectric, but they apply the stress. They are shining light and they keep on changing the force. So you see with the force, the photocurrent is changing. There is a variation in the photocurrent when you increase the mechanical force. It's depending on the direction of light, where it is coming, whether this, and the polarization of the light. They termed it as a flexo-photovoltaic effect. So the theory is, they suggested when you apply this mechanical force, there is an asymmetric distribution of strain in the crystal, which can be used to induce or enhance the bulk photovoltaic effect. And this can be found in centrosymmetric crystals. Now, learning from this another group in Luxembourg, what they did is they used this iron doped lithium niobate. They apply this uniaxial mechanical stress and shine the laser on the material, and they could see a difference in the photocurrent with the change in mechanical stress. They termed it as piezo photovoltaic effect. It is a ferroelectric analogy of the flexo photovoltaic effect. So they suggested that when you apply this mechanical stress, the strain disturbs the symmetry, which leads to this excess photocurrent. It should not be confused with the piezo phototronic effect, where in principle, when you apply mechanical stress, charges are generated because of the piezoelectric effect, and they help in enhancing the photocurrent. So they are slightly different. You could say one is a subcategory of the other, but probably not many reports, or maybe no report on impact on domains and domain walls. So what I did is I decided to study the domains and domain walls in my material K and BNNO with mechanical stress. So here what I did is, this is the surface of my material. It's around 3 by 3 micron, and I applied higher force in this box, short box 1 by 1 micron. So what I did is I applied 1 micronewton here, and I scanned the whole area with 0.1 micron again. So basically what I'm doing is, throughout this scan, the mechanical force applied to the surface of the material was 0.1 micronewton. Then I applied 1 micronewton here, and then I switched back to this force and scanned the whole area. So you can see there are no changes. But if you focus on this image, you see something is here. It's more clear in this. So basically, with the mechanical force, I am actually compressing my material, and we can damage the surface of the material. Having said that, we should be very careful while studying the mechanical impact on these materials, because we don't want to damage our material. We don't want to increase the tip surface contact, because increasing the contact means more charge collection, and that's what we are trying to avoid. So for these measurements, the safe mechanical load was 1 micronewton. So I kept all measurements below this load. Here, what I did is I acquired this image with 0.07 micronewton. No light was shining in dark. I got this red and this blue domains. And then I did scanning of the same area with slightly higher force. And you can see these red domains are shrinking. This is something similar which we observed when we were doing optical polling. When I moved back to the lower force, it's returning. So the effect is reversible. So from A to B, there is some change. B to C, there is some change, but A and C are in principle look same. But interesting thing is this amplitude of the PFM. So in the beginning, I mentioned that this amplitude is an indication of the piezo response of the material. So you can see this change in color. This was like very dark, and then there are some bright, and there are more bright spots. So I did some statistics on these images, and I got this. So this is normalized area of up domains, which are red color domains. So here, this is normalized area. And if I say this as the first scan, the area was around 1, and then it reduced to 0.91, and then it came back. But when we look at the amplitude, basically the piezo response of the material, it was somewhere here. It increased when I increased the mechanical load, and on removing the load, it was supposed to come here, but it is here, which is higher than the pristine state. That means my material is old with this mechanical stress. There is no change in the surface. That means we are not damaging our material. So our finding for this one is that we can mechanically pull the sample even in absence of light. Then I decided to shine light on this. These are again phase images only, not the amplitude. So you see this A image. This is acquired in dark, pristine, nothing done with the sample. And all these images are with this 0.07 micronewton peak force. I shine light. As expected, these red domains are shrinking. And then on turning the light off, it goes back. So this is something which I showed you in the part A as well. But the interesting point is now, after this point, I increase the mechanical load, and you see the difference in C and D. These red domains are shrinking again. On shining the light, again the domains shrink. On turning off, it goes back to the same point. So this F and D are comparable. Again, I did some statistics on this. So what I'm plotting is area of the up red domains. So this is with the 0.07 micronewton. This is with the 1 micronewton. Post optical polling, there is a change. There is a clear difference. I mean, other differences are also there, but that we have already understood. Because of mechanical stress, there is a change in domain population. But when we do both light and mechanical force, there is a change. And that change is again indication of a change in piezo response. I haven't shown here, but Actually, the PFM amplitude changed here again, and we got higher polarization, high piezo response, and as a result, we should expect a higher D33. Therefore, there should be a high photocurrent, and that's what I got in the next measurement. So you see, with different loads, the photocurrent was different, and if we compare with this previous data, where I was using different D33 to get different values of photocurrent. So this is quite comparable. Here we are not compromising the contact area, basically electrode and ferroelectric contact area. So from this, what we can conclude is that a higher force can damage the sample surface. Material will hold mechanically even with the loads of 0.4 micronewton, which is very low. Mechanical stress could change the domain area and tune the piezo response. Light-induced changes are reversible, and photocurrent increases with applied mechanical stress. So we can modulate the photocurrent with applied stress, or the other way around. So with this, I conclude this talk. So we covered the cumulative effect of light and applied electric field. We talked about tuning of material conductivity and how it can induce a photovoltaic effect or tune photovoltaic effect, which can be varied with an applied electric field mechanical stress. So there is a lot more to do, and I am currently exploring this material. What I have not shown is, can we do a full optical study? Can we modulate light when we are applying a light of another wavelength to the same material? And that's what currently I'm looking into. And with this, I acknowledge funding from various sources and support from my collaborators, specifically from the University of Polu, where Dr. Yang Bai invented these materials and provided these materials to us for study. With this, I thank you guys, and I'm open to questions.
Thank you, Gaurav. It's a nice presentation, a lot of good work. Congratulations. Any question? Let's see from live audience here.
I have a few.
May I please take over the hour so people can hear?
So first is you showed those PFM images of the PFM DNA sample, and it was unlike PZT. We could not see the exact polling reversal. So why is that in such materials?
Yes, so that's not fully understood for this material. But when I mentioned that I examined a similar material, so that has surface layers. So basically, when you have a material, only a few top layers are ferroelectric or has this kind of behavior, whereas the rest of the material behavior is different. And even when you remove the top layers, that skin is again generated. So for this other material that I showed, we did synchrotron measurement, and we showed actually that happens. And this is like an intrinsic feature of this particular material.
Because I also tried the same measurements on PLN films, like 15 films, and I observed a similar pattern. I could not analyze it because, and one I was looking for was like exact polarity reversal.
Maybe we can look into that, because that's certainly interesting. We made 10 films of this material, and their response is totally different. It's a monodomain sample in our case, but depends on how you make 10 films. You can have multiple polarization and multiple kind of.
Also, you showed that you can mechanically make all the samples. So, did you apply mechanical stress using the AFM tip?
Yes. So what I'm doing is when we make contact with the tip, we can actually decide the set point where we can increase the stress from the AFM tip.
And the same tip scans over the area.
Yes. So, but with this kind of measurement, one needs to be very careful that tip is not wearing out, because if the tip is very sharp, so say for example in the first measurement the diameter is 30 nanometers, But after a few scans, it becomes 60 nanometers. Then you are collecting more charge because of increasing surface area. So one should be very careful. Even with the higher stress, you can, if there is a little bit of pinching, and the surface area is increased. So yeah.
Also, did you check for the like how much time it takes to get back to its original state, like after mechanical cooling?
It's immediate. Within the next scan. It's immediate. Optical polling takes a bit of time, but mechanical goes very fast.
Thank you. So if anyone has questions over the Zoom, please unmute and you can ask questions.
I have a couple of questions. Thank you. It's very interesting work. So my first question is about if you have you ever tried to shine the light from the bottom of your sample and then measure the surface effect by using PFM?
So
Or
in
you
my,
just
I was always shining from the top because my PFM setup was like that. But when I did a macroscopic measurement, I shine light in the other direction and I was able to depol the sample.
okay. And so this PFM is very sensitive to the contact mechanism between the tip and the surface. And do you measure your sample at close to the resonance of the contact, or just far below the resonance in order to avoid the contact mechanism influence?
So these are all contact measurements. I was tracking the frequency. So we were very sure that the influence is not coming from the sample. It's not an artifact, but it's the real change in the sample.
How can you be sure that it's not artifact?
So what I did is same area again and again with different frequencies, and there were no changes. And what I did is I kept the PFM amplitude for scanning very low. That was 0.2 volts, very low.
That is really low. Yeah. Okay. And another question, can you go back to the slide 9 or 10, maybe?
Yeah.
Oh, not this one. Oh, 10. There is like 3 PFM images.
KPFM images, right?
Or maybe 8. Sorry.
Not
8.
this one?
No. Number 8. This labyrinthine domain structure. You have like 3. This one.
Okay.
So are they like in the same position?
These are all, if you look at this image A, C, and E, they are different locations. But I can do, I did the same thing on same location, and it's reproducible.
Okay, that must be more convincing if it's at the same position.
Yes, but I avoid the influence. For example, if I'm already at this state and I do a measurement, then I'm not sure where the impact is coming from. But I have done that way as well, but I'm just not showing.
Okay, another question is about this polling with full voltage. That is DC polling or AC, like you apply higher voltage of AC. This 4 watts.
This 4 volts was DC.
So you measure the domain structure and then use DC to poll it. While polling, do you apply the AC voltage to scan the image?
No. So what I did is I acquired this image. Then I did another scan. I just applied +4. And after that, I removed +4 and I did this scan, normal PFM scan. So there is no influence of the AC signal on these results.
Okay. And so do you have like the pure polling image, like after apply this forward DC and then you just measure AC without like shining of the light?
Yes, so this A and B are in absence of light. C and D is also in absence of light. All these four are in dark. And this E and F is in absence of any DC field, pure light. So, yeah.
Okay, that means this pole voltage is not sufficiently high to poll your sample, right? If it's not in the same like darkness or pure the light white or dark or black color to induce a single domain. That was what I mean.
Yes, I think I will agree to you on this point, because when you look at this particular measurement between C and D, so you can see the yellow bright domains are gone. That means here we are applying sufficiently high voltage to flip the polarization of these domains here. Yeah.
Okay. Okay. Thank you very much.
Thank you. More questions?
Hi Gaurav, I have two questions if time permit. First question is, could you go to the slide where you shown the P loop with different temperature? Yeah. So could you confirm the phase transition temperature? I mean the structural phase transition temperature for this material?
The structural phase transition was around was above 400, and there is a anomaly at around 170 degrees centigrade.
So this P loop is below the any structural phase transition.
Yes, yes.
Okay. Thank you. Next one is from the maybe the slide where you have demonstrated this performance with a battery cell and light bulb and that plot bar diagram. Maybe I forget the slide number, but yeah, this one. So could you slightly elaborate? I mean, you apply the electric bias and combine with the optical light, and as long as we understand the electric bias effect and the optical energy has the different time scale in terms of the relaxation time or the energy exchange, and you are coupling these two energy to boost your piezoelectric coefficient. So I wonder how it happens to boost the performance so effectively.
How it happened? That's again the point is that I explained in the mechanism of this. When you shine light, charges are generated, which are compensated by the movement of domains. And movement of domains means we are actually changing the state of polarization. So here what I did is like I use this Berlin coat method to study the piezo response of the material. It's a macroscopic measurement. When the sample is not cold, we expect the piezo response to be roughly 0. And when I did this first measurement, it was just exposed to light, no electric field. It changed. So from this, we can say there is a polarization happening just because of the light illumination. And in this measurement, it was a white light source, this room temperature light. And then when I did this electrical and electro-optic polling, there is clearly a difference. So the interesting point is when you say there are different time scales for electrical and optical polling, and probably that's the reason why the effect is not cumulative. It's just scaling by some other factor, which needs a bit of more statistical analysis. Did I answer your question?
Yeah, somehow I understand. Thank you very much.
Did you also study the polarization versus electric field groups in terms of light? Like,
Yeah. So in this Yeah. So here you see the polarization versus electric field, how it is changing. Here I used 405, but if you look at this paper and which we published in 2019, I did this with different wavelengths and different energies. So we see the same kind of trend. There is always a change in the total field, change in the ring rate polarization. And yeah, there is a leakage which has a frequency dependence. Yeah, we did that.
I was just trying to relate, like, show the current density increases when you optically, like, show light to the sample, and the remnant polarization increases. Is there a correlation between these? Like, we say that in ferroelectrics, we say the current density is the leakage charge. So, like, on shining light, the leakage current is increasing in a way.
There are two things. One is actual leakage current. Another thing is when you change the state of polarization, then the current collection is different. So in this material, depending on the time scale, both are happening at particular scale, maybe only one is happening. Usually what people do is when they plot this P loop, they actually have this sort of IV diagram as well. And you can actually correlate that. But we haven't done it.
We are almost 10. So if there is one last question from anyone. We will ask the last question here. So why you selected this 4 or 5 wavelength? That what responds best?
That actually we did with all wavelengths. But the results I'm showing with 4 or 5 because it performs the best because the absorption is maximum. I should quickly mention here that okay, if you look at this particular figure, I only talked about this area where the absorption is maximum. But when we talk about photonic applications or completely optical applications, we don't want this. We don't want any absorption because that's loss. So if you look at this area now, and it's corresponding to this 50 nanometers wavelength, which is actually used for telecommunication. So what you can do is you can change the state of polarization of the material, and you can modulate the incoming light. So basically, you can use it for wavelength division multiplexing, which we use in our optical fibers to communicate. That's another interesting point of this material, but we are working on that.
Very interesting. Okay, thank you so much. It's an excellent work, excellent presentation. And thanks everyone for asking questions. Yeah, thanks again one more time.